This is Dr. Christy Patton-Lukes, and in this set of video lessons we're going to be looking at what impact mixing can have when we form solutions. So, have you ever had that experience where the temperature increases when you mix acids with water? There's a certain amount of energy required to break chemical bonds and a different amount required to form them. So you might think of how much energy it takes to, say, take apart Legos or put them back together. Different amounts of energy are required. If the amounts of energy are almost the same, any noticeable temperature change would be very, very small. Probably you wouldn't even notice it. But for certain materials, say strong acids and water, there's a lot less energy required to break the bonds than there is to form the solution. And in these cases, you end up with a heat of solution, which is the enthalpy difference between the aqueous acid and the individual components, the pure water and the pure acid. If negative, this is going to be heat being released. If positive, heat will be absorbed. So certain chemical reactions or chemical solutions, are going to actually absorb some heat. And those are things that people might use to make, say, a cool pack. So that if you had an injured leg, you might ice down your leg with ice, but you also might, if you were away from ice, use a cool pack, a chemical cool pack. And so there are various ways that we can take advantage of these. Now we're only going to hit the surface of how and why this happens and how we can quantify it in this course. You'll be doing more of this when you study your thermodynamics for chemical engineers. First case we want to look at is sulfuric acid and water, and there's more data in your book. I'm only going to just really emphasize just one or two of these systems. The data is similar, although it's presented very differently. It could be in a table form, and there are different styles of graphs that might be used. So sulfuric acid and water, typically we only are using those in the liquid form, and so this is all for liquid mixtures. And room temperature is 77 degrees Fahrenheit is typically what we assume, and so that is shown here on the graph, and it is this little curve that's just right below that other curve, which is 80 degrees Fahrenheit. And each curve represents a different temperature. Now, we can have different combinations of sulfuric acid with water that goes between 0 and 100%, and that's shown across the bottom axis. Across the left-hand axis, we see the enthalpy of this solution. Now this particular chart is in English units, so therefore it's in BTUs per pound mass of the mixture. The graph isn't continued up into the gaseous phase. It's not continued down where we have freezing forming. And so, all I know is up here I have stuff that's boiling. I probably would rather avoid that. And down below here, I have stuff that's making solids. And again, I would rather avoid that. So we're only looking at the liquid portions of this graph. Now, some of the things that you might notice is, first of all, all these curves have a minimum. And the minimum tends to look like it's around maybe 70% of the acid and the water. Another thing you should notice is that the graph, all these temperature things are very spread apart at lower compositions of acid and water, and they're very compact for the very concentrated acid and water. So now this kind of gets at the question of why in chemistry classes are you always told always add acid? me, being very practical and not liking to wash dishes, it makes more sense to take water and acid. And it seems like if I were to add this direction, then that would be a lot easier because I wouldn't have to wash this container. I'd only have to wash this container. If I add it this direction, then this was dirty, and now then the other one will be dirty also, right? So being very practical and hating to wash dishes, it always seemed to me that you ought to add the water to the acid instead of the other way around. And yet the chemists always tell you always add acid. Well, I actually have made this mistake, so I'm going to teach you so that you can learn from my experience. And this chart here really helps us learn about what's happening there. Because if you do it using the red arrow, okay, adding your water into your acid, then I have something, and we'll say it was 100% acid to start with, and I add just one little drop of water into this acid. So now then the composition is going to be like 99.5% acid, right? So let's think about this. If I am on this 77 Fahrenheit line, and the enthalpy is right around here when it's pure acid, and I add a teeny tiny amount of my water. I bring it a teeny tiny amount this direction, and it doesn't take far for me to see that I'm heating the stuff very quickly, and in fact now I have boiled my water. Okay, that's scary. I've experienced this, so I'm going to tell you. Suddenly you find yourself holding a very, very hot beaker full of very hot, strong acid. It starts to essentially boil, or maybe you caught it a little bit before that, but it gets very, very hot. And so your reaction is to let go. Surely you were doing this over the sink, so not a problem. It crashes into the sink. It was a glass beaker, so now you have broken glass and splashing all over the place very, very concentrated acid. That's why this is a bad idea. So what happens if we had done it the other way? What if we had done it the proper way and paid attention to the lab TA? Well, we would have started over here at pure water, and we would have added a little bit of acid to it. And we see that, yes, it heats up, but not nearly so dramatically. By the time I move over 5%, it's still below 100 degrees Fahrenheit, okay? And I would have time, as I add this very slowly, to let that heat dissipate, and I don't end up with the dramatic heating issues that we had before. So that's why this is something that's an important concept, something that we study, because we know that there's going to be differences in the behavior as we form different solutions. Now for contrast, here's a different situation. This is ammonia and water. This one is not out of your textbook. It's out of the thermodynamics textbook that we currently are using. But this is just to show you some different ways that you can do this. So we can have all liquids, in which case we would have these curves shown like we did before, and they would have a minimum. But they're, not typically at temperatures that people really are interested in studying. We also could have vapors, and we can have curves associated with those. But most of the time with ammonia and water, we've got things where we've got mixtures of liquids and vapors that are being formed. And so we are going to have to deal with that liquid-vapor mixture. And we find that that's another sort of representation. In your book, they also do HCl plus water, and they do sodium hydroxide plus water. And these two behave similarly to the sulfuric acid and water system, not quite as dramatic, however.